Hello and welcome to Lesson 4. This lesson is the first of two lessons that will examine the topic of viscoelasticity in the context of polymer processing operations. The underlying assumption that I'm making is that you're already familiar with the aspects of viscoelasticity that were covered in EPD650, an introduction to polymer rheology. Fear not if this material isn't currently familiar though, as I'll signpost the relevant videos from 640 so that you can revise the subject matter as and when needed. We're going to start by looking at some of the effects that viscoelasticity can impart on a simple extrusion line. The effects I'm going to mention are by no means exhaustive, but the point I want to get across is that the presence of viscoelasticity can have a very large impact on polymer processing, and usually not in a good or a useful way. So, if we think back to 640, we spent a little while talking about viscoelastic flow phenomena. I mentioned a number of flow phenomena during that course, but the two most visual were the Weissenberg effect, or rod climbing, and extrudate swell. Now, the Weissenberg effect, there I have pictured on the whiteboard. You can imagine what you have is a vat of polymeric liquid, maybe a polymeric solution. The solution in question in my measuring jug there is simply wood glue, which is sort of an ethylene vinyl alcohol. And within that vat of liquid, I have a spinning rod. In this case, just a simple piece of M12 studding that's attached to my hand drill. And when that studding is rotating, normal stresses are set up within the liquid, and the net effect of those normal stresses is to cause that polymeric liquid to creep up that rotating rod. When it comes to extrudate swell, what we see is that there's a diameter change between the final product and the die from which that final product came. Now, as you can imagine, for a shape-forming process driven by extrusion, that can be a big problem, and we're going to talk more about that in a second. So the question I want to ask is, how does viscoelasticity affect polymer processing? In particular, what I'd like to do in this part of this lesson is look at an extrusion line and see some of the effects that viscoelasticity has there. Now, if any of the terminology that I've used so far is unfamiliar or is familiar but maybe not current, go please and have a look at the video that I've linked there, which is all around viscoelastic flow effects from a rheological standpoint. So, let's have a look at a simple extrusion line. By now, I no longer need to explain what the extrusion line looks like. We have our extruder, we have our die, we have the product coming out of our die being quenched in a quench bath of some sort, and then we have that product being hauled off by haul-off rollers. So let's have a look at something very simple. Let's consider an incredibly simple extrusion die. Let's say all we've got is a simple contractile die that is taking the diameter of the bore of the barrel down to something smaller. In planar form, this might be a simplified film casting die. In cylindrical form, it might be like a fiber spinning die. So when we think about the flow field within a die such as this, we see three typical things. We see that the pressure drop's different to what we might expect for a Newtonian fluid. If we've measured the shear thinning nature of the polymer, say with a rheometer, and we've got a flow curve, a function of viscosity as a function of shear rate, we may do some quick calculations, as we've seen in the generalized Newtonian fluids part of this course, to estimate what the pressure drop might be in a geometry such as that. And we might find that with a polymeric fluid, actually is different to what we'd expect with a generalized Newtonian fluid. We also might find that the stress field is different. Now, for a viscoelastic material, the stress field will be different, because in a viscoelastic material, stress, of course, is a time-dependent phenomena, not a time-independent phenomena. In generalized Newtonian fluids, the state of stress only depends on the state of current deformation. For a polymeric fluid, it's got stress memory, and so it remembers very nicely its stress history, and so its state of stress at a given time is a function of that stress history. And so stresses can build up over time and stresses can decay over time. We'll examine some of the effects that this can have in a minute or two, but we'll just note here that it can affect quite a few things. Now, the shear rate field is also going to be different. The velocity profiles are going to be different because when, next lesson, we look at polymeric constitutive equations, we'll see that stress is actually a differential equation that features, and it is linked, the state of stress is linked to the shear rate, and again, it is time dependent. We've already seen that the effect of shear and extension, or deformation more broadly, can affect factors such as polymer or chain orientation, maybe even crystallinity if you've got shear-induced crystallization. Now, the reason underlying this, of course, and hopefully you'll recall this, if not, don't worry, we're going to be talking about it more next lesson, is if we think about, say, a simple shear operation. Let's say all we have is let's say a pipe flow with a shear stress. The shear rate tensor might look a little like so. You've just got that shear rate in the 1-2 position there. And of course these tensors are symmetric, and so you see it twice. If, however, we look at the related stress tensor for a viscoelastic material, we cannot ignore the presence of normal stresses. The constitutive equations that we'll explore in the next lesson will again really highlight this. For a given simple shear rate field, such as that gamma dot tensor there, they will have entries in the stress tensor in the normal directions. And so this is fundamentally why things are different. For polymeric fluid, normal stresses are generated by simple shear flows. So you're going to get more effects. You're going to get different stresses acting in different directions. And remember, these are just force per unit area, which means you're going to get fluid accelerations in different areas, which means you're going to get secondary flows, and you're going to get stress fields that are different to what you might expect, which affect the pressure drop. And so those 3 points that I put on the board are all interconnected and all have their root in the structure of the material that we're actually extruding. So one of the effects that these extra stresses can have is something called contraction vortices. Let me illustrate this in the context of a simple blunt-ended extrusion die. I mean, it's very rare to get extrusion dies designed like that because they kind of cause problems. And one of the reasons they cause problems is as follows. If we had a look at the flow field in a blunt-ended die such as that, what we find for a viscoelastic liquid is we actually get a vortex structure developing in that sort of dead zone. We don't see this for Newtonian fluid. And what's really interesting is that the nature and size of that vortex depends on 2 things. It depends on properties of the polymer, and it depends on properties of the process. What we can do is we can quantify that with a non-dimensional group called a Deborah number, dE. The Deborah number here is a measure of the timescale of the polymer divided by the timescale of the process. And if you look how I've written the Deborah number on the board there, lambda there is one of the relaxation times, or a chosen relaxation time for the polymer. It might be some kind of characteristic relaxation time, it might be the longest relaxation time. We know that polymers have a spread of relaxation times, but lambda there is a relaxation time that is representative of the polymer in question. If we look at the quotient of velocity over radius, we'll see that that has units of reciprocal seconds. It's kind of like a shear rate. So that's kind of a quantification of the timescale of the process. And so the Deborah number results from the ratio of those 2 quantities, the relaxation timescale of the material and the characteristic timescale of the process. So contraction vortex formation is dependent on the Deborah number. And we can see that for increasing Deborah number, we get an increasing vortex size, which is rather interesting. And what we furthermore can see is an effect in the parameters of the processes that we can measure. So what we see for increasing vortex size is typically an increasing pressure drop. There's extra circulation there. There's an energy there that's required to keep that going. That energy has to come from somewhere. And so what we measure instrumentally is an increased pressure drop as a result of that. What we also find is that within this vortex, the polymer residence time is going to be increased. If you've got polymeric liquid trapped in that vortex, it's going to be there for a lot longer time scale than the material flowing through the die and out into the extrudate. That can be problematic because over time polymers can degrade thermally, they can start to gel, They can sometimes have some kind of crystallization depending on the polymer, depending on the rates of strain. And so what we can end up with is a material inhomogeneity. For those of you who have played with extrusion lines, you can see these gels come through from time to time that really do spoil, sometimes wreck, the nature of the product. And these contraction vortices are a good place to generate those gels because you've got polymer there exposed to heat for a long period of time that may well be gradually degrading. So the Deborah number of the flow is an important ratio to know about, and for very high Deborah numbers, what you find is that these vortices become unstable. I've pictured 3 stable vortices there. Well, I've pictured them as stable because it's a non-animated picture. You don't know if they're stable or not, but those are actually stable vortices. If we've actually got the full picture of the die, because I've only put half of the die on the screen there because the die is symmetric, for a stable vortex we'll have a symmetric vortex pair. For an unstable vortex, that vortex pair will oscillate, and those oscillations can influence what happens downstream of the die. And so if you've got an unstable vortex pair, you can actually end up with downstream process instability as well, which directly affects the shape and form of the extrudate. So contraction vortices are important to know about. If you ever do any viscoelastic modelling of polymers in contraction flows, you'll see that trying to resolve these vortices computationally is actually quite a challenge, because you need to A, be aware that they're there, and B, make sure that the mesh density that you put in those regions is sufficient to capture it. And being mindful of that, if you look very carefully at the images I've put on the board, you'll see that there are actually multiple vortices present. The big image at the top actually is 2 vortices. You've got the very big obvious vortex, but you look incredibly closely at the corner, there's another tiny little vortex embedded there. And this is problematic when it comes to numerical modelling, because if you can't fully resolve that vortex in the corner, you're probably not going to get your simulation actually to converge. So it's problematic from a practical standpoint, and it's problematic from an academic standpoint as well. So let's think about extrudate swell. I mean, the raison d'etre for most extrusions lines is to produce a product, a shape-formed product out of a die. And what we'd like to be able to do is to uniformly make these products. So extrudate swell is a factor that disrupts this in a way. Let's remind ourselves first of all what happens in a Newtonian fluid. We find that for different Reynolds number ranges, Newtonian fluids will also change their shape once they leave a channel. We find for very, very low Reynolds numbers, the die swell is there, evident. And this is because you're getting a velocity profile rearrangement between a parabolic flow within the duct and then a plug flow out of the duct when there's no retarding wall to give a velocity profile. And the ratio between the extrudate diameter dE and the die diameter d maximizes at about 1.13, so about a 13% swell for a Newtonian fluid under creeping flow conditions. Under inertial flow conditions, but still laminar conditions, what we find is the opposite. We find a diameter reduction of about 13 or so %. And this is the sort of thing that you might be more familiar with when you see, I don't know, honey coming out of a squirty honey jar, for example. Water coming out of a tap is also a good example, but the inviscid nature of water means that very often you're going to the turbulent regime there. Whereas with honey, you've got a nice viscous liquid at a Pascal second or so viscosity, and so you can clearly see that filament decrease in diameter as you squeeze it onto your toast in the morning. So viscoelastic liquids exhibit orders of magnitude die swell sometimes. So 13% is the highest you get in Newtonian fluid, a few 100% you might find in a viscoelastic fluid. I've illustrated the effect here with a cylindrical die. If you're extruding cylinders, pipes or rods, then there's some established theory that allows you to estimate the level of extrudate swell you're going to obtain. And if you look at that expression closely, it's an expression due to Tanner, you'll find that you need to know information about the normal stress, the first normal stress difference, N1, and also the shear rate of the material, both of which are evaluated at the wall of the die. And that rule of thumb is a quick way to give an estimate, and I emphasize estimate, of what the extrudate swell is going to be. But imagine what you're actually extruding is not a rod or a pipe, but a complex cross-section. I don't know, maybe a bit of curtain rail or some other functional component. Then the shape of the component is going to be grossly affected by swell. And so trying to design an extrusion die to make a particular shape has to take into account how the material is going to swell. And swelling as well depends on Deborah number. So it depends on the polymer and it depends on the process. And so we have to be rather careful if we're shape forming complex materials, because the die design may be different for different materials because of the rheological properties of the materials and the way they store stress and the way they swell. So complex cross sections in extrusion dies are quite difficult to get right. It's quite an art form, but there's a lot of computational tools in the modern era that allow us to design that with little more care. So I've already hinted at the fact that processing lines can become unstable when I was talking about an oscillating vortex pair in that blunt-ended contraction. So if you're running an extrusion line too quickly, typically bad things happen. That's a very overarching rule of thumb. In more detail, the type of instabilities that you're going to see are numerous, and they depend both on the polymer architecture and on the characteristic timescale of the process. It's coming down to those two things again. I'd like to give an example. So for a linear low density polythene, for example, which hasn't got a great deal of chain branching, then if we plot a graph of stress as a function of shear rate across an extrusion die, we see some quite interesting behaviour. First of all, we see what looks like classical shear thinning, except that it's not entirely classical shear thinning, as I'll outline in a minute. Then we tend to see a region where we get unstable flow, and the pressure oscillates quite a little bit. After a certain shear rate's passed, those oscillations stop, but the stresses are lower than when you entered the oscillating region. In fact, the stresses oscillate between the minimum and the maximum stresses, the maximum stress being where you enter, the minimum stress being where you leave. And then you get a sort of increase and plateau of stress once again. Okay, so at the moment, one might say, yeah, all right, that's a bit strange, but so what? Well, the so what part of it is because each of these regimes infer a different kind of characteristic on the extruded product. So if we look at regime number 1, this is probably where we want to be operating. We're getting well-behaved, stable extrusions. And you can see in that picture there that you've got a nice rod of polymer being extruded from the die in the downwards direction. If we go into region 2, what we actually start to see is a surface instability coming into play. This surface instability is called sharkskin, and it affects the opacity of a polymer. If you look under the scanning electron microscope, what you see is there's very, very minute and periodic ridges on the surface of the polymeric material, which interfere with the path of light. This might not be a problem for applications where optical properties are unimportant. Then perhaps you can live with sharkskin. For cast film lines, for example, where optical clarity might be important, this can be a major limitation. If we look at region 3, we see something really quite interesting happening. In this pressure oscillation region, you get all sorts of strange periodic extrudates. Sometimes this is called a stick slip, sometimes. But what you can see is spirals or other kinds of periodic patterning in the extrudate. And typically by this point, the extrudate is no longer fit for purpose. Exiting region 3 and into region 4, we have a region what is called superflow, where you've got what appears to be a stable extrusion, but there may be defects, quite large defects as you can see there in the picture, that manifest from time to time. So it looks stable, but it's actually not, and it's perilously close to region 5, which is where everything tends to fall apart, and the stresses are so high in the polymer that you end up with a region called gross melt fracture. And by the time you reach gross melt fracture, you're binning product. It's going to be complete waste. So we need to be aware that the rate at which you process a polymer is important, and equally as important is the type of polymer that you're actually processing. So we can see that typically these kinds of instabilities are built up by stress. And what's really interesting is if you try and put mitigating factors in the way to stop stress build-up, you tend to delay the onset of these instabilities. So this is really, really neat. So if we can understand the origin of something, we can then work to try and remedy the problem. And typically, if we think about the flow through an extrusion die, you've got, or we've assumed at least, you have no slip boundary conditions between the fluid and the walls of the die. That imposes your shear rate, that imposes the stresses, and the faster the polymer goes, the higher the stresses build up, and it's at that point we start to get these stress-related instabilities occurring. So if we can somehow lubricate the die to prevent that stress build-up, then we might be in with a chance of eliminating or at least postponing the onset of these instabilities. And experimentally, you do actually see this. So lubricated dies can be manufactured typically by putting a coating on the die, for example, a silanol, and that effectively introduces a partial slip condition. And with a partial slip condition, your shear field is going to be less, your stress field is going to be less, and consequently the onset of the process instability is postponed, which is fantastic. The final thing I'd like to just bring into your consciousness at this point is the problem of residual stress. Up until this point, we've talked a lot about the flow of the liquid phase, when the polymers melt in the melt state, and how it's flowing through the die and how it might be subject to vortex formation or extrudate swell. But we need to think as well that viscoelastic liquids have time memory. And so they remember stress. Stress takes time to build up. Stress also takes time to decay once the factors that cause the stress, a shear rate field, have been released. So this really concerns the polymer as it exits the die. We'll see that extrudate swell is part of this stress relaxation process, but we need to consider it beyond just that. So if we think about a typical, very simplified stress profile within the liquid, if you're processing a polymer melt in an extruder, you're going to be building stress. There's lots of deformation going on. Depending on the design of the extruder, there might be kneading elements or conveying elements or pumping elements. All that is shearing the polymer and stressing it. Then you've got flow through typically a contracting die. That's where the majority of your pressure drop will lie within your extrusion line, and so the shear rates and the stresses associated with that are very, very significant. Once the polymer's exited the die, it goes in an instant from being in a very, very, very high shear environment into being into a no shear environment. The only thing it might experience is some extensional deformation. And so suddenly all those stresses that are built up have the opportunity to relax. And so those are the two parts of the curve that I've put on the board there. You've got your stress build up through the extrusion line and the die, and then you've got your stress relaxation subsequently once the extrudate has emerged. But typically what we do is we quench a product and then deal with the product in its solid state. So if we quench a product too quickly, what we end up doing is storing stress in the solid phase because we just haven't allowed that polymer to relax enough before we solidify it. This might not be a problem. For whatever application we have, stored stress in the polymer may neither be here nor there. However, there are some applications where stored stress is a problem. And let me give you 3 examples. If we have a polyester yarn and we quench it too quickly and we lock in stress in that yarn, if we make some clothing out of that yarn and then put it in a hot wash, the clothing is going to shrink as all the stresses relax. What we might also find is that polymeric components, high precision polymeric components, may lose their tolerances with heat and with time. So, for example, if you've got a polymer that might be, for example, injection molded into a mobile phone case, we all know that mobile phones get pretty warm from time to time, depending on the processor load, and we'll keep them for, 2, 3, 4, 5, 6 years. And over that time frame, if there's stored stress in the injection mold, that periodic heating will just give the chance for that stress to relax a little bit, and you might find that the injection molded parts just don't clip together very well anymore. On the subject of mobile phones, if you've ever done what I've done and dropped a phone down a toilet or had it caught in a thunderstorm, then you try and dry it out with a hairdryer afterwards, only to your dismay that the SIM card tend to become shaped like a crisp. because of the amount of stored stress that is in that product. So let's summarize a few key points. The main thing I wanted to get across in this part of this lesson was that viscoelastic polymer melts are processed, and that viscoelasticity can impact the way in which the processing happens. So we've got effects such as normal stresses, we've got effects such as extension hardening, we've got stress memory effects, we've got stress relaxation effects. A lot of these we'll be talking about in the next lesson. And these are fascinating from an academic standpoint, but a real pain from a manufacturing standpoint when you actually need to make something consistently to the correct tolerances day in, day out, year in, year out. And so the key point here really is that viscoelasticity in relation to polymer processing operations is quite a challenging phenomena to work with.